Good day, students. Welcome to the second recording of the module Food Proteins. In this recording, I'll be focusing on the protein structure, the 4 different levels of the protein structure. Before getting into the actual content, I would like to remind you that we are following a certain chapter outline, and in this recording, we're going to focus on the 4 levels of a protein structure and then the classification thereof. So as we already mentioned earlier on, that the protein structure is actually made up of amino acids that are joined together to form a polypeptide by means of a peptide bond. So now in terms of the protein structure, we then talk about the 4 different levels, and those 4 different levels are as follows. We have what we call the primary, secondary, tertiary, and quaternary level of the protein structure, and each and every level actually builds on top of the other. Like when the primary forms, then on top of the primary the secondary forms, and then so on and so on. So you can see on the right hand side it's actually showing all the different 4 levels of the structure, but what I'm going to do now is I'm going to go through each of them to explain how do they form and their significances. So starting with the primary structure. So what makes up the primary structure? The primary structure is what we have actually been talking about ever since I started with these recordings. First of all, the primary structure are those simple monomers, which are your amino acids that are joined together in a certain sequence to form a long polypeptide chain due to the peptide bond that actually connects them. So the most important thing about the primary structure would definitely be the how many of those amino acids are there, so that's the number, and then the sequence, which amino acid follows which one. And the sequence is a very important thing in terms of determining the type of protein that will form in the later levels. Okay, so what I mean is, in terms of the different levels, there's different types of bonding and interactions that are taking place. And one of the most important bonding or interaction that takes place later in the latter stages of the levels would be whereby the R groups. Remember we mentioned the R groups? The R groups are those side groups that actually make each and every amino acid unique. So in the later stages or the later levels, that's whereby the R group participate. And when they participate, certain types of R groups react with each other. So depending on the sequence and how far they are from each other, then the protein will align itself and fold and twist and turn to make sure that those R groups that are far apart from each other then usually come and form a bond. We'll talk about that later. So like I already mentioned, the primary structure is very important. It determines the level of a protein structure. Let's just make an example of yourself and myself, or everybody that went through the education system. In primary school, in grade 1, maybe you learn how to count or to read. And then in grade 2, then you do something. So each and every time you build on the level. So if you can't read in grade 1 or you can't write in grade 1, it affects what happens in secondary school. Same applies to the primary protein structure. So whatever happens with the primary structure, it obviously affects what happens later with the other tertiary and quaternary structure. So you can already see on the far right this picture that's actually depicting a primary structure where you can already see there's 25 amino acids that are joined in a certain sequence. That sequence is glycine is the first amino acid. The second one is proline. Threonine is amino acid number 5. Cysteine is 10. And lysine is 15. So that is the sequence for that protein. So if it happens that glycine moves and goes to amino acid number 2 and proline comes to number 1, that now becomes a totally different protein. So that's why we normally talk about the sequence. Okay, so in terms of the importance of sequence, I'm just going to make an example with the 2 phrases that you see down there. It says, talk little, do much. Okay, so there's actually 4 words there that are being repeated, or we can say they're not actually being repeated, they are being twisted around. So talk is one amino acid, little is one amino acid, do, and much. However, when you actually move the position of each of those words, what you actually end up with is a totally different meaning. So talk little, do much. Do little, talk much. So obviously it becomes a different meaning, completely different. So in that way, that is how we explain the primary structure and the importance of amino acid sequence. One other example that we can make, just moving out of food science and technology, getting into the medical side of things. If you guys know your red blood cells, I don't know if you've ever heard about sickle cell anemia. That's whereby the red blood cells have a different shape to your normal ones. So your normal red blood cells are globular in nature, and we already know that those red blood cells contain what we call your hemoglobin. Hemoglobin contains iron, and it obviously attaches with oxygen and transport oxygen in the blood. However, what happens is that the normal hemoglobin protein, one of the protein, has that arrangement that you see there. So the fourth amino acid is threonine, proline, and the sixth one is glutamine. However, when you have what we call a sickle cell, the red blood cell, instead of having that glutamine there in number 6, it's actually substituted with valine. It's obviously due to a gene mutation. So in that way, it changes that protein, and that is why the shape of the sickle cell red blood cell is actually not globular. It looks like a moon or like a sickle. You know what a sickle is. So in that way, it actually reduces its functionality, because, you know, when the red blood cells are round and globular, they can move around throughout without being impeded. But when you get those moon-shaped sickle cells, they don't flow easily, and usually that is why those people usually they feel fainty, because they're not getting enough oxygen to get where it is. And that was due to the fault in the primary structure, altering the normal sequence. So you can see how important the primary structure is. Okay? So then, from the primary structure, so the primary structure is the first one. So whatever is formed on the primary structure is the basis. But then that primary structure then graduates into secondary structure. So it doesn't mean that when it comes to secondary structure, then the structure has to break down. No, it does not break down. It just builds on top of that. So what happens in the secondary structure? So the secondary structure is already known as the higher level of protein structure, because it's obviously higher than the primary. So in the secondary structure, what actually happens is that the protein starts to fold. So when the protein folds, it folds on its own, or it happens that maybe there are many aligned proteins there that then fold together. I'll just show you an example just now. So these proteins actually fold due to what we call intramolecular forces amongst those residues. The residues are obviously the amino acids that are joined together. So in the folding, so when the polypeptides are folding, it's due to the hydrogen bond that forms between them. And that hydrogen bond forms between the amide nitrogen and then the carbonyl oxygen. So that's the hydrogen bonding that takes place there. So as a result, then you find that there's a whole lot of those hydrogen bonds that are formed, because there are so many of that amide nitrogen and then the oxygen of the carbonyl compound or the carboxylic group. So in that way, you form a very strong structure, because we already know that hydrogen bonding is very weak. What makes them strong is because usually when they form, wherever they're forming, there are a million, there's a whole lot of them. So in that way, it becomes strong. So this hydrogen bonding that forms, obviously, like we mentioned, it forms between the amide nitrogen and the carbonyl oxygen. When they form in there, they can either form in one polypeptide, as you can see there, that winds up on its own, or one that winds up in that fashion. I'm just still going to talk about which ones are those. Or you can find that it's two polypeptide chains that are separated. So it's chain 1 and chain 2, and then the hydrogen bonding is forming between those two. So when hydrogen bonding forms between one chain that is coiled around on its own, that is known as intramolecular hydrogen bonding, because that bonding is taking place within that one molecule. However, in instances where you have a polypeptide chain on its own and then another second strand, and then hydrogen bonding between those two takes place, that is called intermolecular hydrogen bonding. Inter for international, if you know what I mean. Okay, so in this secondary protein structure, it's characterized by either what we call the alpha helix. Here's the alpha helix. The alpha helix is actually a molecule that looks like a spring or the telephone cord. Okay, and then we also have what we call the beta pleated sheet, which is this two. Those are the beta pleated sheet. But as I already mentioned, then with the beta pleated sheet, we actually have either one that coils up on its own, or you have two that are lined together. And sometimes we have what we call a random coiling. Random coiling is not a usual thing. It usually happens when you have those bulky amino acids, especially things like your phenylalanine that usually contain those aromatic side chains that then take up space within the molecule, but that's not mostly common. Okay, so we're going to first start talking about the one protein structure, the beta pleated sheet, because I already mentioned under the secondary, you have beta pleated sheet, and then you actually have the alpha helix. So we're starting with the beta pleated sheet. Like we already mentioned, with the beta pleated sheet, it's actually characterized by inter and intramolecular hydrogen bonding. As I already mentioned there, you can actually have two structures whereby hydrogen bonding is forming between them, or you can form one that is actually winding around on its own. So what happens is that in terms of the beta pleated sheet, so we mentioned that there's hydrogen bonding that's taking place. So we already mentioned that the hydrogen bonding takes place between the hydrogen of the amine group or of the amino group, and then the oxygen, the double bonded oxygen of the carbonyl group or the carboxylic group. So everywhere where you're going to see the double bonded oxygen and the hydrogen of the amine, that's when the hydrogen bonding takes place. Like I already mentioned, it's strong because there are so many of those forming around. So we have what we call a parallel beta sheet and anti-parallel. So a parallel beta sheet is usually characterized by when you have one polypeptide and another second polypeptide. Okay, so they are going in the same direction. However, when you have an anti-parallel beta sheet, is usually when they are going in the opposite direction, or it's one that winds up around on its own. So that's the beta pleated sheet, and usually these are characterized by what we call fibrous proteins. I'm still going to explain more about that. So that is your beta pleated sheet. So here's just a structure of the beta pleated sheet that I drew for myself. I hope you guys can actually see what it looks like. So there is your N-terminus, and there should be a C-terminus somewhere here. But obviously you know that in terms of a protein, there must always be a free amino group and a free carboxyl group at the end. And you can already see there the hydrogen bonding. There's the hydrogen bonding taking place. And there is this beta pleated sheet coiling around on its own. So with this one, because it's one sheet that is coiling around on its own, this one is actually characterized by what we call intramolecular hydrogen bonding. Okay, so carrying on, then the secondary protein structure will be the alpha helix. So the alpha helix, like I already mentioned, it is shaped like a spring or like a telephone cord. Okay, so this one, unlike the beta sheet, it's actually stabilized by only intramolecular hydrogen bonding. So it's only the hydrogen bonding that's taking place within one polypeptide chain that is wound around on its own. So do you see? There's the hydrogen, there's the oxygen, there's the hydrogen bonding. And you can see there's a whole lot of those. That is why I already mentioned that those bonds are quite strong. Okay, so there you have it. You have your hydrogen bonding, and then what happens in terms of the alpha helix is that each complete turn, where there's a 10, there's a complete turn after every 3.6 amino acid residue. So let's just round it up and say after 4 amino acids, then there's a turn that it's forming that alpha helix. And some of these proteins can either be what we call globular and fibrous. Okay, so when we talk about globular proteins, globular, we think about the globe. The globe is round. Think about fibrous, fiber. The fiber is obviously long chains and stuff like that. So things like, let's say, making an example of collagen. You guys know what collagen is? Collagen is found around the bones. We also find it in skin. So if you are starting to get wrinkles, it means that your collagen is degrading, and obviously that happens when you get old. That is why ladies usually go for a collagen fix, because obviously of the collagen that's actually degrading. Okay, so collagen are what we call structural proteins. I mean, that is why it gives your face structure. That's why it gives your bone structure. And then we also have keratin, which is also a structural protein. Think about your nails. Think about your hair, the keratin Brazilian, what do you call it? The Brazilian blow or whatever, blow dry, whatever you call it. So that's that. So here what you are looking at, this is the alpha helix, but this is the secondary structure. But now on the right hand side, it's showing you when the quaternary structure, which is the highest level, has already formed with at least 3 of those single alpha helixes, but we'll talk about that as the time goes. Okay, so we said it can either be globular or fibrous. Look at the globular protein like myoglobin, globin, coming from the word globular protein. And then we come to the tertiary structure. The tertiary structure is the 3rd level. So what happens is that we mentioned that secondary structure is folding of the polypeptide chain. However, in the tertiary structure, the folding is even more compact. So it's folding of the polypeptide chain into closely packed, almost spherical shape. Okay, so it's becoming tighter and tighter. And the reason for that is because in the tertiary structure, the bonding that takes place is usually due to your side chains interacting, because we already saw there the amino group was involved and the carbonyl group was also involved in 2 reactions, whereby they're involved in hydrogen bonding and also still involved in terms of forming the peptide bond. But the side chains were doing nothing, just waiting for a job. So now in the tertiary structure, that's when you realize that the side chains are now going to interact with each other, depending obviously on certain factors. Those we're obviously going to talk about. But for now, what happens is that in the tertiary structure, in terms of this compact or closely packed spherical shape, this actually takes place due to the 2nd law of thermodynamics. So you guys still remember your physics. What happens is that the protein, what it does, it confirms to a structure that is thermodynamically most feasible. So that's actually the highest disorder of the protein, but the protein functions very well at that disorder. I think I usually, when I want to explain this, I always think about yourself or myself or anybody. When you come from school or you come from varsity, you get home, you were probably dressed in school clothing or whatever clothing, or I'm dressed in teaching clothing. When I get home, the first thing I want to do is to take off those clothing, take off my hair if I have a weave, sit and just be comfortable and put maybe my leg on a table. And then I'm so comfortable and I feel relaxed. So that is my natural conformation. However, that's some form of disorder. Now disorder because my hair is facing the other way, my leg is up the table. So that's actually the highest entropy. But that is the state in which I am more relaxed. So same applies to the protein. At that stage, that is when it's very relaxed and it can function the best. So what happens there? So in the tertiary structure, the amino acid residues, remember we spoke about sequence, that these amino acids are in sequence. Those amino acids that are far apart from each other, like if we go back to this structure here in the primary, let's see if we can come back here. So each and every of these amino acids obviously contains their side chains. So what happens is that the side chains actually want to interact. So let's look at one here. We have cysteine in number 10. Usually cysteine will want to align with another cysteine, which there's only one cysteine here. Okay, let's say lysine and glutamic acid. There's no glutamic acid. But anyway, so what happens is that, oh yeah, so your lysine at number 15 would actually want to align with glutamic acid in number 7. So it means that this molecule is going to wind out around so that that lysine gets to that glutamic acid. But I was just making examples, so I'll just show you with another different structure so that I don't actually confuse you. So what happens is that the side chains now interact. So no matter how far the other chain is or the other side chain, it will make sure that it comes closer to the other one. So in this tertiary structure, it's then stabilized by the covalent and non-covalent bonding or non-covalent interactions, and usually that's when we form your globular proteins in the tertiary structure. So here is the tertiary structure. So this whole diagram is actually showing you all the levels together, but it actually outlines the tertiary structure in a nice way. Okay, so in the tertiary structure, what is happening? I'll say it again. The side chains are interacting, and they interact based on their forces of attraction. So the type of interactions that we have in the tertiary structure, number one, we have what we call the hydrophobic interactions. So what happens is that all the amino acid residues that are hydrophobic, they would want to line with each other and form a pocket, because we already know that the hydrophobic pockets will always be on the inside and then the hydrophilic ones on the outside. If you also think about the cytoplasmic membrane, if you still remember the lipid bilayer, where you have the hydrophobic head or tail, I'm not thinking straight now, but the other ones, the tails actually line up together far away from the water. So stuff like that. So, okay, that was a bad example, but anyway, something closely related to that. So the hydrophobic amino acids, they come together and then they form a hydrophobic pocket far away from the water because they don't associate with water. So there's the first one, the hydrophobic interactions. So hydrophobic interaction, you see it with the side chains that contains methyl ends. Here's another hydrophobic one, number one. Number two, you have what we call the ionic interactions. So the ionic interactions are also known as the salt bridge. Okay, ionic interaction due to forces of attraction between negatively charged side chains and positively charged. So positive and negative, they come together. So then they form what you call a salt bridge or ionic interaction. That's number two. And then number three, there's what we call the disulfide bond. The di for two sulfides. So wherever there is a cysteine and another cysteine amino acid residues, they line up together to form what we call the disulfide bridge. Sometimes they call it the disulfide bond or the disulfide bridge. So this is the disulfide bridge. So that's the third interaction. And then the fourth interaction, that's where we actually find hydrogen bonding again. So the hydrogen bonding there is now being formed between either the side chain and a peptide group. Or you can also find whereby the side chains themselves are actually forming a hydrogen bonds with each other. Okay, so this is likely serine, and this is what is this one? What do they call this one? This is histidine. So they then form together and form a hydrogen bond between the amide hydrogen and then the oxygen of the hydroxyl group. So it means that the tertiary structure is actually based on at least five possible interactions. So the first one is the hydrophobic interaction. The second one is the salt bridge, or what we call ionic interaction. The third one are the disulfide bonding. And then the fourth one are the hydrogen bonding. So hydrogen bonding can take place between the side chains, or it can be a side chain and then the peptide groups on the actual polypeptide chain. So that is your tertiary structure. That does not mean that the previous secondary structure also gets damaged, but tertiary structure takes precedence. So when the feasibility of a secondary structure to form is more than that of the tertiary is more than that of the secondary, but some of the secondary structure may still remain, provided that there were no interactions that were taking place between the side chains. So that is now your protein structure. And then what happens is, in terms of, we already mentioned that when the protein folds and twists and turns in that compact size, especially in the tertiary structure, that's what we call the natural conformation. That's when the protein functions at its best. Okay, so usually what happens is that we all know that proteins don't exist just on their own. They are found in food products, and most food products contain water. So what happens is that when the protein is folding and folding, most of the times, or all the time, the hydrophilic R groups of any globular proteins will be on the outside, forming hydrogen bonds with the water. And then the hydrophobic ones, will be on the inner surface, shielded away from the water. And one of the most important aspect of your tertiary structure is that the disulfide bond that forms obviously between the cysteine and cysteine is very important. It's also very important in insulin, but we don't work with insulin. So let's talk about something that we work with all the time. So in terms of in bread baking, so when in bread baking, the protein in there, when it comes in contact with water in the bread, there's what they form the cysteine disulfide bond. However, what happens is that that kind of dough becomes hard and it's not easy to work with. So the important is, when you are kneading, the kneading of the bread helps in terms of what? Breaking the cysteine bond. And usually to do that, they will add additives. They will also add in cysteine, so that it actually helps in improving the dough structure, and it works as a reducing agent. I know you probably did this in food tech too. So the addition of L-cysteine as a reducing agent, so that it breaks down the disulfide cysteine interaction, and then it helps in terms of getting a dough that is workable, and it increases the loaf volume, so it's got the best dough structure. And then also the second thing in terms of the tertiary structure would be the globular nature of the enzyme. So when the enzyme functions like lipase in its form, it's actually in its tertiary structure with a certain active site that forms. That's where the reaction takes place, and that is due to its natural conformation, which is characterized by obviously certain amino acids that are joining together. Okay, so to move over, the quaternary structure. The quaternary structure is the last level. It's not that complicated. So it's characterized by non-covalent association of proteins. So what happens is that it might just be different proteins that are not identical. They come together. And then an example will be the actomyosin, that is actin, the protein actin, and the protein myosin that come together in the meat muscle, whereby it helps in terms of contraction and relaxation of the muscle. You'll still learn about that in meat products. Casein micelles of milk, which is very important. However, what happens is, when the protein is in its natural conformation of the tertiary and quaternary structure, what happens is that it can be denatured. Okay, it can be unfolded, when we actually apply external factors, whether that is due to mixing, due to heating, due to freezing. So it can do that, and then it can change its natural conformation into something else that might help in terms of its functional properties. We are actually done with the structure. So I'm just showing you the different quaternary structure, where you have your triple alpha helixes, and then you have hemoglobin that contains 4 different chains, 2 beta chains and 2 alpha chains. So they come together and form this quaternary structure. And then class exercise, an easy class exercise. I'm going to also put this on Blackboard. It's which one of the 3 different shapes is the linear protein chain most likely to adopt when it's actually dissolved in water. I'll explain more about this one on Blackboard. And then lastly will be the classification. The classification is a very easy thing. So based on the protein and how it behaves, it can be actually classified into 3. This is something that you can go read on your own. So we have what we call simple proteins, conjugated proteins, and derived proteins. So the simple proteins is just a protein that contains only the amino acid. So it's just a straight chain that just has amino acid 1, 2, 3 up to whatever, and that's it. However, when you have conjugated proteins, it is still a simple protein in terms of its structure, but then it is attached with something else that is not protein in nature. So it can either be a carbohydrate, it can be a lipid or nucleic acid. Derived proteins, on the other hand, it's when the protein is modified by either chemicals or enzymatic method, and then something new is formed. So depending on the extent of modification, you can have what we call primary and secondary derivatives. Okay, so go read about this. In this here, these are actually your simple amino acids. You can see some of the simple amino acids there. Your albumin, which is found in egg white or in milk or in legumes. You've got the glutealins that I was talking about. Their solubility, they are found in wheat or in oryzanin in rice, especially very important for dough formation. But we'll talk more about this when we talk about functional properties of proteins. There you have the conjugated proteins, conjugated phosphoproteins, lipoproteins, glycoproteins. So the actual protein thing itself tells you what is it conjugated with. Lipoproteins is conjugated with lipids. Where do we get those? We get lipoproteins in milk and in egg yolk. In terms of functionality, this lipoproteins helps a lot when we talk about emulsification. So that's where functionality comes about. There are your chromoproteins. Chromo means color, and we have our hemoglobin, obviously, and myoglobin that gives the red color of either meat or blood. And then lastly, then we talk about the derived proteins. These are actually proteins that have been modified by chemicals or enzymatic methods, and we rely on these types of methods to get food products like cheese, whereby milk, a liquid milk, becomes solid cheese. So that depends on the type of process that you are applying, and depending on the extent of that, it can be a secondary or primary derivatives. Okay, so thank you very much for listening. See you on the 3rd recording.